In the third lecture, we learn about the thickness measurements of thin films. We will learn about thickness measurement by quartz crystal monitor and by optical interference methods. The properties of almost all thin films are thickness dependent. Reproducible properties are achieved only when the film thickness and the deposition parameters are kept constant. In many applications, particularly so in the case of optical devices such as interference filters, anti-reflection coatings, etc., the success of the fabrication depends only on the deposition of specific thickness of the dielectric layers. And the measurements can be done either in dynamic or static condition. In the former, the thickness is measured during the deposition process, while in the latter, after its completion. The direct and easy way to determine film thickness D is to measure the weight of the film that is deposited on the substrate. Knowing the film mass M, the deposit area A, and film density ρf, we can calculate its thickness D as equal to M over A times ρf. Values of D so obtained are imprecise because the film density is not known with certainty. Hence, we proceed for more accurate techniques to measure the thickness of thin films. The first technique that we are going to learn to measure the thickness of thin films is by using quartz crystals. In a quartz crystal monitor, the rate of evaporation and thickness is often controlled by the quartz crystal thickness monitor. The figure that you see on the right is that of a thin film coating unit inside which we have placed a quartz crystal sensor. Because of its simplicity and sensitivity, this method has become a standard in various thin film fabrication processes. Now, on to the principle behind this technique. Homogeneous elastic plates set into mechanical vibration have resonant frequencies that depend on their dimensions, elastic moduli, and most importantly, density. Additional mass in the form of a deposited thin film alters or lowers the resonant frequency by effectively changing the properties of the composite vibrating plate. This is the principle that underlies the use of crystal oscillators to measure film thickness. In the quartz crystal monitor, we'll use an AT-cut quartz crystal, that is a crystal that is cut approximately 35 degrees with respect to the z-axis is used. On both sides of the quartz crystal, metal film electrodes are deposited. It is then mounted within the deposition chamber close to the substrate. The fundamental frequency f of the shear mode is given by f equal to Vq over 2 times dq, where Vq is the velocity of the elastic transverse waves normal to the crystal plate and dq is the thickness of the crystal. If a mass dm deposits on one of the crystal electrodes, the thickness increases by an amount given by d equal to m over a times ρf. When we substitute for d in the expression for f, we have f equal to Vq over 2 times dq. So this is equal to Vq over m times a ρf. A change in frequency due to the deposition on the crystal can be obtained by differentiating this equation with respect to m. That is, dF equal to VQ times A times rho f times minus 1 by m square times dm. So this can be written in terms of f as minus f by m times dm. Now we'll rewrite this equation by multiplying with f over f. This gives us minus f square by m times dm times 2m over vq times a rho f. So this is equal to minus f square 2 over vq times a rho f times dm. We will introduce a constant c which is equal to vq divided by 2, and this is defined as the frequency constant whose value is 1656 kilohertz millimeter in 80 cut chords. So the final expression becomes df equal to minus f square divided by c rho f times dm over a. The negative sign in this equation signifies an increase in the frequency as the added mass increases. We see that df is directly proportional to f square. This indicates that higher sensitivity can be obtained for higher frequency. This figure shows the instrumentation of a quartz crystal monitor. The material to be deposited is heated in a coil. So when it is heated, vapors come out and get deposited onto the substrate that is placed directly above. What you see in green here are quartz crystals. To control the deposition, we have a shutter which could be moved using a motor. Other instruments include a shutter control, thickness monitor, and a rate monitor. An oscillatory quartz crystal with natural frequency at 6 MHz is positioned inside the vacuum chamber above the source and by the side of the substrate in such a way that vapor is deposited both on the substrate and on a defined area of the crystal surface. A second crystal having a natural frequency slightly different from the first one at around 6.5 MHz is mounted in the control unit outside the vacuum chamber. The difference between the crystal frequencies is amplified, fed into another circuit where it is mixed with a variable oscillator to produce a final difference frequency of between 0 to 100 kHz. In some cases, the difference frequency is directly noted by a frequency counter. The mass of the deposited material causes a reduction in the natural resonance frequency of the monitor crystal, causing an increase in the final difference frequency. The change is converted to a DC signal which actuates both the frequency shift meter and the rate meter. Thus, the thickness of the film and its rate of deposition are displayed on the meters. After the end of one deposition, the frequency shift meter is brought to zero by adjusting the variable oscillator frequency. Depositions can then be added to monitor crystal up to a limit of the final difference frequency, that is 100 kHz, although some crystal ceases to oscillate within 100 kHz. In this setup, it is imperative that the crystal sees the vapor source. Because of radiation, its temperature is bound to increase. Also, the heat of condensation of the vapors during the deposition will warm the crystal. Hence, suitable radiation shield should be provided to protect the quartz crystal. N0 corresponds to the refractive index of air, N1 that of the film, and N2 that of the substrate. If the substrate is air, then N2 is taken to be N0. So we consider a beam of light that is incident at an angle theta from a medium of refractive index N0 onto a film of index N1 and thickness T that is deposited onto a substrate of index N2 with N1 between N0 and N2. The reflected light will show an interference maximum for a wavelength lambda when the path difference between the successive beams reflected at each surface, that is 2n1t cos theta, equal to m lambda, where m is an integer. If n1 is greater than n0 and n2, the reflected intensity will show a minimum, that is a dark band, when 2n1t cos theta equal to m lambda, and maximum if 2n1t cos theta equal to m minus half lambda. An interference maximum will produce a characteristic hue of the film. When white light is used, the reflected light will show maxima for various wavelengths for which interference condition is satisfied. And this is the basis of the visual method of monitoring film thickness, and this was realized by Newton as early as 1675. A spectrometer may be employed to measure the transmitted or reflected intensity as a function of the wavelength and thus record positions of maxima and minima. Let the mth order maximum occur at lambda 1 and the m plus 1th order at lambda 2. At normal incidence, the refractive index is the same for lambda 1 and lambda 2. Then 2n1t equal to m lambda 1, which is equal to m plus 1 lambda 2. When we rearrange this equation, we'll get 2n1t equal to lambda 1 lambda 2 over lambda 1 minus lambda 2. If we know n1, it is very easy to find the thickness. And this is a very accurate technique to measure the thickness with less than 1% error. The optical methods with interferometers. When two highly reflecting surfaces are brought into close proximity, interferent fringes are observed when the assembly is viewed in monochromatic light. Such optical interference methods are commonly employed for film thickness measurements. Wiener was the first to use interferent fringes to measure film thickness. The interference fringe method have been developed to a remarkable degree by Tolansky and are now accepted as the absolute standard methods. Two types of fringes can be used for thickness measurements. The multiple beam interference, which is also known as Fizeau fringes of equal width, and two beam interference. We will now discuss about these two. Fizeau fringes of equal thickness. The Fizeau fringes of equal thickness are obtained in an optical apparatus of the type shown in this figure. The interferometer consists of two slightly inclined optical flats, that is optical flat 1 and optical flat 2, one of them supporting the film, which forms a step on the substrate. So this part of the instrumentation is zoomed in here. You can see that the film is deposited on the substrate or the optical flat 1 in a step-like fashion. The surfaces of the optical flats are highly reflecting, and for that, on the optical flat 1 as well as on the film, a thin layer of aluminium or silver reflection coating is provided. The upper flat, that is optical flat 2, must, however, possess an observable transmission. When the second optical flat is brought in contact with the film surface and the interferometer is illuminated with a parallel monochromatic beam at normal incidence and viewed with a low power microscope, dark fringes can be observed which trace out the points of equal air gap thickness. The two adjacent fringes, in this case, will be separated by lambda by 2, where lambda is the wavelength of the monochromatic light that is used. If the optical flats are brought very close to each other, the reflected fringe system can be seen to consist of very fine dark lines against a white background with a fringe width which can be made as small as lambda by 100. By adjusting the relative positions of the flats to form a wedge-shaped air gap, as you see in this figure, the fringes can be made to run in straight lines perpendicular to the steps on the opaque film. So in this figure, these dark fringes corresponds to the upper surface which consists of the film and the substrate. And this part of the fringe correspond to the lower surface which consists only of the substrate. The fringe show a displacement delta as they pass over the film step edge, and this displacement delta expressed as a fraction of the lambda by 2 fringe spacing gives the film thickness. The thickness can be measured to about a tenth of a fringe. Note that it is necessary to coat the film as well as the exposed glass surface with the same reflecting layer in order that phase changes on reflection from the two sides of the step will be the same. The two-beam piezointerferometer. Instead of using multiple beam interference as in the preceding case, one may use an interference objective arrangement with a beam splitter to produce two-beam piezointerference fringes. So as shown in this figure, we have a source of monochromatic light which is split by a beam splitter, a part of which gets reflected from the film surface and the other part from the reference plate. And both these beams superpose to produce the interference pattern which could be observed using a microscope. While this arrangement yields relatively broader fringes and hence less accuracy, the optical flat does not physically touch the film so that it does not get scratched. Furthermore, a reflecting overlayer or a step is not required, which makes this technique very useful and convenient. Using this technique, thicknesses as low as 100 angstrom with an accuracy of 20 angstrom can be measured.